So in my last video, I was talking about bond types. So talked about things like ionic bonds and metallic bonds and covalent bonds. And so I'm going to pick up now talking about bond polarity. So bond polarity is related to covalent bonds. So remember that covalent bonds are those bonds that are between two atoms who are sharing electrons with each other, right? So so we've got covalent bonds, the electrons are shared between each other, but the thing is that not all atoms share electrons equally, okay? Just like small children, they don't all share the same way, they don't all share nicely. Atoms don't all share nicely when it comes to their electrons. And so let's take a look at what kinds of things can happen. So there's the first type of covalent bond we call a non-polar covalent bond. This is where electrons are shared equally between the atoms. And so the most common non-polar bond is when you've got atoms of the same type. And this makes sense if you think about it. So for example, we've got two hydrogen atoms. These two hydrogen atoms are going to equally pull on the electrons. They're going to equally share those electrons. This is going to be the same for any sort of elements that are in a covalent bond where they're the same. So that's one way that we can get this to happen. So that's one way that you can get a non-polar covalent bond. Another thing that can happen is if you've got atoms playing tug of war with each other. So for example, we had in our previous video, we had carbon in the middle of a bond with oxygen on either side for carbon dioxide. I know, I'm not the greatest at drawing with a pen. But we had carbon with oxygen on either side. These aren't all the same atom, but the oxygen on this side is going to pull just as much as the oxygen on that side for the electrons. And so this would be considered non-polar because everybody's kind of sharing equally. Everybody's kind of pulling the same amount on those electrons. So it's an equal tug of war. When we have an unequal sharing, this is where we get what we call a polar bond. Sometimes you'll see it written as a dipole, di for two, because you've got two different poles, two different places where the electrons are being pulled on. And so this most commonly happens when you get different atoms in a bond. So here you can see now instead of two hydrogens, we have a hydrogen and a fluorine. And now you've got electrons around the hydrogen, but more of the electrons are going to be found around the fluorine. That's because the fluorine is better at pulling on those electrons. And so some of the elements are much better at pulling on electrons than others. So let's take a look at which elements are better at pulling on electrons than others. So this is an electronegativity table. Electronegativity is just the ability of atoms to attract bonding electrons. So it's comparing their ability to each other on how good they are at pulling on those electrons. The higher the value, the greater the attraction. So the higher the number, the more they're going to pull. So you can see here, the noble gases, these guys have dashes. That's because they have no electronegativity. Again, they have those full valence shells. They're not going to be attracting anybody. They're not going to be doing any bonding. So let's take a look at the other ones. So we've got hydrogen here. It has a 2-2. It's kind of out of place with a lot of the other members on this side of the table. Because if you look, except for things like beryllium and manganese, or I'm sorry, magnesium, manganese is down here, Beryllium and magnesium, pretty much everybody else is below 1 until you get over here until the metals. So hydrogen's kind of an exception, but if you notice, the electronegativity is low over in this corner, and then as you go across the table and up to the corner here, generally the electronegativity goes up. And in fact, these guys right here have the highest electronegativities on the periodic table. So nitrogen, oxygen, fluorine, and chlorine are going to be the ones that are the most electronegative. The next one would be bromine. You can see that one's almost 3. These guys, if they are in a bond with another atom, they are going to pull on the electrons. And the one that we most commonly are going to see is going to be oxygen. You'll see nitrogen sometimes, but a lot of the compounds that we see, especially with living organisms like ourselves, is oxygen. And so the way I think about it is oxygen's greedy. Oxygen loves electrons. And so oxygen's going to pull on those electrons whenever it's in a bond, and that is going to make it more electronegative. It's going to actually give it a negative charge on the side of the molecule it's in. So, for example, if we get our little water molecule back up here, remember it's the oxygen with the 2 hydrogens on it, the oxygen is going to tend to pull the electrons towards its side because it's electronegative. It likes those electrons. It has that super high number compared to hydrogen. And so that's going to make this side of the atom just a little bit, so that's a little bit, negative. So it's a partial negative over on the oxygen side. But that also makes the hydrogen, because remember hydrogen has protons in the nucleus, 1 each. That's going to give the hydrogen side a partial positive charge. And so this is why we call water a polar molecule, because it has a slightly negative charge on the oxygen side and a slightly positive charge on the hydrogen side, because that oxygen atom is pulling on those electrons because oxygen loves electrons. So let's talk about why we care. Why do we care about polarity? Well, the thing is that polarity dictates the chemical and physical properties that we talked about in a previous lecture for, that's not what I wanted to do, for any material. So if, you know, a molecule is polar, or if a molecule is nonpolar, it's going to dictate how that molecule works as far as what it's going to interact with as far as other molecules, but also just things like boiling point. And this is because of things like this. So for example, nonpolar molecules are very weakly attracted to each other. So you can think of polar molecules like a magnet. So polar molecules are like weak, well, not weak, they're kind of weak magnets. But if you've ever played with those kind of cheap magnets before, polar molecules are like that. They are attracted to each other. You can pull them around, but you can pull them apart, right? Nonpolar molecules, they like to hang out with each other, but they are not going to like to stick around with each other. And so, for example, we've got over here nitrogen gas. So nitrogen gas is a nonpolar molecule because it's made up of 2 nitrogens. And let's think about what this does to the boiling point of molecules. And nitrogen gas is a great example because I'm hoping that most of you have seen demonstrations with nitrogen gas before. So nitrogen gas right here where it's being poured is nitrogen at negative 196 degrees Celsius. So not Fahrenheit, Celsius. So it's much colder than what you are thinking in your head. So think about that. To make it liquid, we have to drop the temperature to 196 degrees Celsius. What happens as soon as we expose that nitrogen liquid to the atmosphere, to regular room temperature? It turns into gas, right? It immediately becomes gas. It will immediately start boiling and turn into gas very quickly. And this is because those molecules are so weakly attracted to each other. You can see here in the picture, most of them aren't even stuck together, right, in that liquid form. They are just kind of close to each other. So the boiling point for nonpolar molecules is really, really, really low. If you take a look down here in the table, we've got polar molecules and nonpolar molecules. The boiling point for all of the nonpolar molecules is in the negatives. And not just like a little bit, a lot, right? I mean, the one that is the closest to zero, and this is in Celsius, so 0 is the freezing point of water. The closest one is carbon dioxide, and that is dry ice. So even think about dry ice. It's a solid when you pull it out, and it turns immediately into a gas. So this one has, this really, really low boiling point. So do all these other ones. So, but yet our polar molecules, hydrogen fluoride, water, ammonia. Yeah, ammonia has a boiling point of negative 33. How do we use ammonia as a cleaner? We mix it with water. So the ammonia that you have in your house, that is actually only part ammonia. And it will actually eventually evaporate out of your bottle there. So these polar molecules, because they have that positive negative charge to them, are very attracted to each other and will stick together like those little magnets. This also affects things like the solubility of materials. So what do I mean by this? Well, polar molecules are only attracted to other polar molecules or charged ions. So think about what can dissolve in water. Right? Things that can dissolve in water that are really good at dissolving in water are things like salt and sugar. Those are usually the two that come to mind for everybody. Well, we know that salt is ionic, right? Because it's NaCl. When they come apart, sodium is positive, chlorine is negative. And sugar is polar as well. It has positive and negative charges on it. The molecule is like water. It has positive and negative regions because of oxygen and hydrogen. Can you dissolve anything in water? No, right? Think about it. I mean, it's something like nail polish, or paints. Most paints are not dissolvable in water, and that makes sense because we don't want them to dissolve in water. But they are going to be able to dissolve in other things. So this solubility has to do with what kind of molecule are they. Are they polar? Are they non-polar? And so that's why you have to use different types of solvents in order to dissolve different materials. All right. The last thing I want to just talk briefly about is compounds, as far as their names and so forth, because we're going to see these going forward, because we've made compounds using these different bonds. So when we want to make a compound, as far as the formula goes, we're going to use the atomic symbols from the periodic table to represent the elements. So if you see a compound formula and you're not sure what the element is, you can always look this atomic symbol up. So for example, lead is Pb. You might not know that that's lead, so you can look that up on the periodic table. The subscripts are going to represent the number of atoms for each element. So the subscripts are the little numbers that show up. So for example, we saw CO2 as one of the materials that we were looking at as far as atoms go. So we've got carbon and oxygen. The subscript is this little guy. So that tells us that there are 2 atoms. 1 is assumed, so that's why there's not a C1O2. Right. And let me erase that. So what does that mean for sodium chloride? It means that it contains 1 sodium and 1 chlorine, because there's no numbers down here. And then for this compound, we've got 1 nitrogen and 4 hydrogens. All right.